We're here at a conference about the physics of events and the physics of observers. So naively, people would think about an event as something that just happens in time, a change in time. So, I mean, if you think of the conference as an event, it's lots of people suddenly coming together in the same place. So why is that idea of an event not good enough for physicists? Why do you have to probe deeper to understand what an event is?
Yeah, this is one of those things where we have a very good everyday intuition for what things are, that there are events that happen at a particular time and place. They don't unhappen. Once they've happened, that's it. They're done. And that they can happen without anybody knowing that they happened. They could happen, far away where nobody knows. And if one happens, you and I would agree that it happened. So there are these objective, sort of time directional things that occur and don't unoccur. And we're used to that. Our life is kind of made up of lots of these events, and we sort of know some of them, we observe some of them, and some of them we don't. And that all seems pretty straightforward. And indeed, physics, as it was kind of originally created back in Newton and Galileo's time, they thought of the world in much this way. There were things out there that were moving around in space, planets. They based their first physics on planets. And there was an objective world that they could describe with mathematics. And it didn't really matter so much who was observing it. There was an objective world out there that we could study. Now, this everyday notion of events that we have, and an everyday notion of observers that may or may not observe an event, that the event can be off over there and we can see it, but we don't affect it. Those notions have kind of gone out the window with modern physics. So what physicists discovered in the early 20th century is that it's much, much more subtle than that. That in our best theory of the very small universe called quantum mechanics, that if for something to happen, we sort of need an observer to do something. We need to make a measurement of something. And if there's no observer and there's no measurement, nothing really happens. There's a mathematical description that kind of proceeds, but there's no happening. And when something happens because you observe it, the observer is very intimately involved in that. There's no measuring something in quantum mechanics without affecting it. So something happening becomes this much, much more subtle and interesting thing where there's an interaction between a system and an observer, and the observer is part and parcel of something happening. So the whole picture is different. And the aim of this meeting and sort of why we're here is to really go into that, to really understand what exactly happens when you measure something in quantum mechanics. It's a famous problem that nobody really understands. And what does it take if you're an observer and you observe something in quantum mechanics? What does that mean? Do you have to be a conscious observer like us? Can it be just a machine? Can it be a little tiny thing like a bacterium or something even smaller? What counts as an observer? And if only some things count as observers, why not others? So all of these things are kind of problems that physicists like to brush under the rug. They're hard, they're complicated, they're subtle, and we don't like to think about them because we'd rather just do calculations about supernovas and about the Big Bang and make better lasers and stuff. But they're there, and part of the interest in this conference is to really bring those out into the open and spend some time thinking hard about them, because they're super interesting and super subtle. And I think we can actually learn a lot about other parts of physics if we understand these things better and kind of get them out of the closet.
Mm-hmm. And there is also a problem with the notion of time, isn't there? Because, again, like when we think about events, we immediately think about time. When is it happening? How long does it take? Yeah. But there isn't really a notion of time in fundamental physics in the same way.
That's right. So if we think of, there's the future that's made up of things that may or may not happen. They haven't happened yet. The present, things that are happening now. The past are things that have happened. All of those have to do with happening. So there's three different types of happening. And the sort of fundamental description of physics, if you just talk about, I've got some atoms and they're moving around according to the laws of physics, there's nothing like that. There's no things that happen, really. There's no stuff that hasn't happened or stuff that has happened, or even direction of time. If you run the same physics backward in time, it looks just the same. You can't tell.
So basic physics is such as running, like the analogy is often shooting a billiard ball on a table. If you run that backwards, you wouldn't be able to tell.
Exactly.
So,
and
that's
if you
the
could
lack
zoom
of-
way into sort of atoms and you forgot about quantum mechanics a little bit and just saw atoms zooming around, you'd never know if you turned the film
So there
backward.
isn't a direction of time really inherent in the fundamental
In the
physics.
fundamental laws of physics, and yet it's obviously here, in this room, things happen and don't unhappen. And that's a real puzzle in physics, how exactly you sort of bridge that gap between the world that has all those things, events happening, observers, observations, direction of time, and this fundamental physics description that doesn't seem to have any of those things. They're seemingly real, so where do they come from?
And that's why you're here to figure out.
That is what we're here to figure out, hopefully at least a little bit.
Thank you.